Hey everyone, and welcome to the sixth video on the p-block elements and their compounds. And this time we'll be looking at group 17, or the halogens, which in my opinion are one of the more interesting groups. So group 17, as I said, it can also be referred to as the halogens. These are right on the right hand side and consist of fluorine, chlorine, bromine, iodine and astatine. They're all non-metals and exist as X2 molecules. What I think makes them really interesting and quite unique in the p-block for sure is that all the states of matter are present in the group. So fluorine and chlorine are gases, bromines are liquid, which is super rare on the periodic table, and then iodine and astatine are solids. They all readily gain an electron to form halide ions, X-, and this is because the electron gain enthalpies are all positive, so they really like gaining an electron, really like being that anion. They can also form covalent bonds as well. In the oxidation states, fluorine is just always -1 because it is the most electronegative element. It'll always just take that electron. And the other halogens also show -1 because these, as we go down the group, even though the electronegativity decreases, with the halogens it's still pretty high, especially for things like chlorine and bromine. So they can also show -1, but they can also show things like +1, +3, +5 and +7. So going through the fun facts for each of them, fluorine is one of the most reactive compounds in the periodic table, if not the most. I've got two videos demonstrating that here if you want to see some reactions of it. So the first one is just fluorine gas at room temperature being essentially blown on some charcoal. So no match or anything, just blowing the gas onto charcoal and a fire starts. And the second one's quite a fun one because it's a fluorine, which is, as we said, the most electronegative, most reactive non-metal, with cesium right at the bottom of group 1. It's the most electropositive element and the most reactive metal. So that's a fun one. It's as I just said, most electronegative element. It's also the most oxidizing element. So there's this oil rig thing I showed once before to say what oxidation and reduction is. So oxidation is loss of electrons and reduction is gain of electrons. So fluorine is the most electronegative, so it really likes to gain an electron. It itself gets reduced, but it has to take that electron from somewhere, and wherever it takes it from is oxidized because it's lost an electron. And it's the most oxidizing element because it's the most electronegative, so it can actually oxidize oxygen, which is what we saw when we in the last video when we saw the OF2 and O2F2 compounds. Oxygen had actually been oxidized in those. It's produced from the electrolysis of HF in molten KF, so it's quite similar to how we saw electrolysis of some of the other elements we have made. And it's so reactive it can form compounds with inert gases, so like the noble gases, and we'll see more about this in the next video. Chlorine's still pretty reactive. It's found mainly in sodium chloride, so salt, table salt, sea salt. And it's also in a lot of organochlorine compounds, so like PVC, the white plastic that's around glass for windows, for example. That is very chlorine rich. Bromine, as I said, very rare in the fact that it is a liquid element. The only other one is mercury. And iodine is a solid that readily sublimes to form violet vapor. So sublimation, very much like dry ice, so CO2 does it as well. It's going directly from the solid to the gas phase without any liquid in between. And these are both obtained from seawater. So the Dead Sea concentration of halide ions is much higher than normal seawater, so 5,000 ppm versus 100. And because of this, the Dead Sea you float much easier in. Now, don't ask me the science behind this. I'm going to say buoyancy is physics, so I shouldn't know. But I just know that in the Dead Sea, loads of it's very, very salty, but you float a lot easier as well. So that's interesting. Trends down the group, the elements become less oxidizing. This is because they get less electronegative, and the bond dissociation enthalpies decrease down the group because of poor orbital overlap. Fluorine is an exception to this. Fluorine's got a really weak bond. The FF bond's really easy to break, lower than expected, and this is because there's a lot of electron repulsion there. And these last two things all lead to the standard trend we've seen throughout the periodic table, that when things form halides, they become less stable as we go down the halogen group. So it's a combination of the fluorine is a really weak bond, so it's really easy to break, and it has a much stronger bond enthalpy with whatever else it's reacting with. So let's look at the oxides of the halogens. We've already seen a couple in the last video on oxygen, so XO2 and X2O2. Yeah, we've seen these on the last video. But some higher oxidation states are possible with chlorine, bromine and iodine. So fluorine can't do these, but the other three can. And this is because fluorine is more electronegative than oxygen, whereas the others aren't. We can get things like ClO2, Cl2O6, Cl2O7. So this one's a yellow paramagnetic gas. And you remember, as I said, paramagnetic was having an unpaired electron, and therefore this will also interact with a magnetic field. Cl2O6 is a dark red liquid, and Cl2O7 is a colourless oily liquid that's shock sensitive and will explode. And they're all acidic. So let's take this Cl2O6 is a really nice example. It reacts with water to form two different oxo acids. So yeah, if you remember, the oxo acid is like the oxo anion we were looking at earlier, sulfates, carbonates, in this case perchlorates or chlorates, and the oxo acid just has the charge offset with a proton, which makes it acidic. So Cl2O6 reacts with water to make two of these oxo acids, and the reason for this is that Cl2O6 is a really interesting ionic solid. So remember, when we were looking at ionic solids, it was usually something like NaCl, and they had this crystal structure with say sodium being the cation and chlorine being the anion. But in this case, it's actually a mix of two chlorine oxygen ions. So you've got, I'll try and write it down here, ClO2 is the cation, and then ClO4 is the anion. So this has an ionic structure like NaCl, except this time the cation and the anion are both chlorine oxygen ions. And that's why when it reacts with water, one of these, the cation, grabs the oxygen from the water and a proton, and then this one just grabs the other hydrogen. So yeah, interesting oxide. Now it may come as a surprise, but we can actually look at the halogen halides, and these are called interhalogen compounds. So yeah, halides of halogens. And these are, in my opinion, the most interesting part of the halogen chemistry, and also probably the most important for the exam for a couple of reasons. So the first one is that we can predict their shapes using VSEPR, and they're really good for this. Like I've got some examples down here of various chlorine with fluorine, bromine with fluorine, iodine with fluorine, and they all perfectly follow the rules for VSEPR. And yeah, you can get all of the shapes imaginable. So yeah, they're really good for that. And it also shows all the oxidation states of the halogens. So we talked earlier, they can be like -1, +1, +3, +5, +7. If we look at these examples again that are following VSEPR, in this case, so the rule is that fluorine is always -1, which makes it super easy to calculate these oxidation states as well. In this case, we've got ClF, so a chlorine has to be +1. Chlorine trifluoride, so chlorine this time will be +3 because there are 3 F minuses. Bromine, if it's a BrF5, would be a bromine in the +5 oxidation state. And iodine, if we've got IF7, will be in the +7 oxidation state, which is a super high oxidation state. So yeah, that's one reason why the intelligent compounds are really interesting, but also very good to know for this course, because they're very good examples of calculating oxidation states and molecular shapes. So these can actually be prepared from the just reaction of the elements, and the products will depend on the stoichiometry and things like the conditions. So if we react chlorine with 3 equivalents of fluorine, we get chlorine trifluoride, and if we react it with 5, we get chlorine pentafluoride. As chlorine trifluoride is, as it comes to dangerous chemicals, this is the one. Like if you Google what's the worst chemical in the world, or what's the most dangerous chemical in the world, this will probably come up. So I've given a quite entertaining YouTube video link here that shows why. It reacts with literally everything, and the products are again, like HF that I was saying before is a horrible, dangerous compound. That's actually the product of this even more horrible, dangerous compound reacting. So yeah, very dangerous, but very interesting chemistry. And finally, we can also get ions of the interhalogen compounds. So as well as having like, ClF, we could get ClF2 plus. Yeah, so instead of the 3, 5, 7, whatever, we get the even numbers with the positive charge or negative charge. These can be created in two ways. So cations are done by reacting a neutral interhalogen, so something like I was saying, like ClF, ClF3, BrF5, so one of the odd numbers essentially, with a fluorine ion acceptor, such as arsenic pentafluoride. So this actually means, so a fluoride ion acceptor is actually something that will take an F-. So in this case, the arsenic pentafluoride will take an F- from the ClF3, and then you're ending up with ClF2 plus. And you can do the same to get an anion. So in this case, you'd react it with a fluoride ion donor. So it's exactly the opposite thing. In this example, we got cesium fluoride, and this is something that gives away the F-. So we'll just end up with a cesium cation and ClF4-. So there's the interhalogen compounds. Very interesting chemistry, and very important.